time, so we'll record it so that people can see it later if they would like to. And welcome. So yes, I will sit here and answer whatever questions you all would like to ask. Did you all have any questions?
So just to check on the final, half of them are content-based in the true false, and half are resources you've given us finally.
Yeah.
Okay.
Yep.
That makes sense. So I would get some of this. Whoa.
Yeah, a lot of them are not things that you would be able to exactly figure out without looking at the resources.
Like an evil way to practice thinking like an evil practice.
Yep. Yeah. I don't know if there's a non-evil way to force people to practice that. Yeah, I would say that most, at least historically, most of the points that people miss happen on the true-false parts and not the free response parts.
And the true false will be scored the same way, like if you get it wrong.
Yeah, so exactly. So I don't know exactly what the plus minus breakdown will be, but they'll be equal to each other. If you get the wrong thing, you'll get the minus points, and leave it blank, you get 0 points. And they will be intentionally worded trickily so that trying to lure you into selecting the wrong one. Welcome. We were just talking about the true-false point values on the exam, that if you get an incorrect one, you will get marked negative points, and leaving it blank for 0 points.
Is the total score capped at 0 points?
It would be possible to go negative on the exam. It has never happened before, though. Any other questions?
Our exam like 64 points in total?
That is an excellent question. I haven't written it yet, so I haven't fully decided. Yeah, the intention was that it was going to be double the midterm. The midterm was 32, so yeah, 64. And yeah, the midterm grades were very good. Lots and lots of full credits. Probably, my hope is the grades would be just as good for the final, but probably not. I think it'll be significantly harder than the midterm. Is that a question?
Yeah. And when we're making indexes, and I guess this sort of goes with this time.
Yep.
Do whatever. We have a where clause. That is what we're searching for, looking for where goes first.
Hold on a second. I'm just going to bring up a blank page here so that I can write down what I think you're saying as you say it. So you're saying that there's some sort of create index, and the index itself has the where clause. There's things here, and then the where clause as part of the create index command.
Oh no, I was going to do like the query trying to speed up as a where clause.
Okay.
But
so something like select and then a where clause here. Okay.
So you have like select a where B is something, right, from the table.
Mhm.
Where we have this, this most, sorry, the index, would be create index on whatever table we're doing.
Mhm.
B, A.
Yep, table, then you'll always list whatever equality constraints first. So here we just have one, so then it would be B. And then you can have, let's add some more things here. B, C equals something, D equals something. And then we'll have like an E greater than or equal to. And it doesn't matter the physical order that these are placed in inside the where clause of the select. These can be in an arbitrary order down here. But the equality conditions should always go first, B, comma, C, comma, D. The actual order of these doesn't matter. Order doesn't matter because they're all equality constraints down here. And then you can have at most one inequality in your index here. And then, so doesn't matter because they're equalities. Then here we have one inequality, one inequality, and then whatever your, just the auxiliary information that you're storing so that it's an index only scan. Just writing this out in green so it's color coded, the A here, and then let's add in F into G, and then so the F comma G comma A, put right there. And again, the order of these doesn't matter either. This will allow for the index only scan right here. The equality constraints over here in particular allow you to zoom in onto the inequality constraint really quickly. And then the last things over here, that just auxiliary information in the index, that are the things that you're selecting over here. If we had an order by clause here, an order by clause, then if you're ordering by any of the things that you have an equality constraint on, that's totally okay because you'll just have one of those things. But the order by and the inequality up here should be the same. So if you have both of them, then they should be the same. Or if you only have one, then that's okay. But those should be the same. And the order by here doesn't matter whether it's ascending or descending. The order doesn't matter here because the way that B tree was structured, you can either go down to the leftmost portion and go to the right, or go down to the rightmost portion and go to the left. And you can do both of those two things efficiently right here. Does that answer your question?
I guess like to add on to that, if you have the group by as well, we want to put that before or after the where.
Yes.
Okay. It would have to be one of the things you selected.
If we have a group by, then yeah, just the physical location of the group by, I think, has to go right here. The group by clause. And then ideally we would want whatever we are grouping by to use well, we have two algorithms for doing group by. There's two algorithms. There's the hash and the aggregate. And the aggregate, assuming our data comes in sorted order, is faster. And so we would like to have our data come into this in sorted order, whatever we're aggregating on. And so in this case, if we have the inequality or we have the ascending descending, those are this column right here is the only thing that we can sort on. And so we'd want our group by, or our group by would have to be on the E column here to be the most efficient possible to come into the aggregate already sorted. If we had a group by here and it was not on the E column, then we would have to pick one of these things that we can't be efficient with. We'd have to either do the hash or not get our order by down here in sorted order. Question? Screen is not shared. There we go. Sorry, Zoom people.
So not do the order by or not do the.
So here the inequality, the order by, and the group by, in order to make each of, in order to make any one of those three things efficient, they would need to be the last thing in our create index up here in order to be able to get things out in sorted order. And the inequality here and the group by and the order by will all be more efficient if the index gives things in sorted order. But you can't sort by multiple columns at the same time. And so if you have these three, group by, an inequality, and an order by in your in the same query, then you can't achieve an index only scan with the aggregate group by algorithm in any form with the create index command. Those are just an incompatible operation. But if all three of those things are the same, or if some of those things are missing, then you can get the fast index only scan with no additional sorts or anything. Does that make sense? Sort of? Okay. Yeah.
I have some follow-up questions. So if they're not all the same, they're not that I like to share, then you just have to pick which one you want as the last. Like, do any of them work or is it?
So yeah, let me make this a little bit more concrete. If we have a select a where b less greater than or equal to some value, group by C, order by D, so 4 different columns over here, then the best query, the best index that you can do depends on exactly which choice of algorithms is going to happen here. If we had, say, create index on whatever our table is called, and then it's B comma A, this index right here will allow these two parts to go faster, allow your where portion over here to go faster. And usually that's the thing, that's like the most, the things in your where clause are the things that are going to be the most important to speed up, because this is actually filtering out rows. So it makes the whatever subsequent downstream steps are, makes those faster. Postgres could choose to do the group by before doing the where selection. If it did that, then the index would look something like create index on table C. That would having C be what you're indexing on means that it could efficiently do a group by with the group aggregate first, and then do its filtering on B and sorting on D. But probably doing the filtering up here with an index like the blue one over here on B first would be more efficient. For the purposes of the final exam, I'm not going to give you a question where, or I'm not going to give you a SQL query where there's a conflicting situation like this. This would be the sort of query that if in the real world you are running into saying somehow needing to write a query like this, then you would redesign your schema somehow so that this situation doesn't come up, and all three B, C, D here would be represented by the same column somehow. So I'm not going to ask you that sort of thing on the final exam.
Could we also like do a partial index instead of the where? Be able to speed up.
Yeah, so this is a great question. So here I was not talking about partial indexes at all. So the partial index is where we include the where clause actually in our index itself. And the partial index will never speed up, or the where portion of the partial index would never match your group by clause or your order by clause. But if the where portion down here exactly matches your where clause up here, then it will speed up. So here, the where be greater than or equal to 10. If we include this constraint already inside of the index, then this would speed up those three lines all together like that with a partial index like this. So it is possible to speed up that portion right here with this red index down here. Without this, without the where clause line right here, it would not speed up that line right there. In practice, the partial indexes are very rarely used, because in order to use a partial index, you have to hard code the value over here. You must hard code this. And the reason it must be hard coded is because Postgres needs to know what this value is right here at the moment of creating the index. And so your actual SQL query has to have a hard coded value over here. And usually your SQL queries are going to somehow be dependent on user input. And so it's rare to have a situation in practice where you're using these hard coded values. I haven't written the final exam yet, so I don't know for sure whether there'll be a problem with that requires a partial index to make it faster. But I would say there would be like a maybe 1 in 5 chance that a partial index would be the solution to a problem. You know that a partial index, the hint that a partial index might be the solution to a problem is that if your where clause, again, if your where clause has a hard-coded value like b greater than 10 inside of it, then maybe partial index. But if it has where b greater than some user specified value, like that, definitely not partial index. And the operator over here doesn't matter. I just selected greater than because that's what I was using above, but the operator doesn't matter. The thing that's important is whether the value is hard-coded into your query or not. So it's the thing over here that I have to the right-hand side of your operator. The operator itself doesn't matter. So it could be equals or like or whatever else. Other questions about the select clauses and speeding them up? Maybe here's a question. So let's say we have some sort of select some columns, say A, B, C, and from some table where D equals something, and then I add a limit 10, some sort of limit clause over here. What are the table scanning strategies that can take advantage of the limit clause? This says limit right here. That M and the I kind of got merged together, but that's a limit here. So what well, maybe I'll phrase that differently. Here, if I say create index on table D, will this index make the limit go faster? So I chose this blue right here because that would be an index that could enable an index scan on this query up here. And so if we're doing an index scan on this query up here, will we get the results faster down here using the limit clause? Does the question itself even make sense? Like what I'm saying? Sort of.
That like you need an index only scan.
It's true that an index only scan can take advantage of the limit clause over here to go faster. And so if this index over here was modified so that it had the A, comma, B, comma, C inside of the index, then we could do an index only scan as available. And the index only scan will be sped up by the limit clause. We can't do an index only scan with this index right here because these columns over here that we're returning aren't actually part of the index. And so we have to touch the heap table pages in order to find the A, B, and C columns right here. And so we have two other table scanning strategies that we could use to do that, taking advantage of this index. One is the index scan, and the other was the bitmap scan, or the bitmap index scan. And with this query up here in this index, we could use either the index scan or the bitmap index scan in order to use this index on this query up here. It turns out the index scan returns elements one at a time. And so because the index scan returns things one at a time, it can stop after it's returned 10 things. And so this here will make the query faster. or we'll take advantage of the limit clause. Take advantage of limit, and this one would not take advantage. The reason this doesn't take advantage of the limit clause is because it has to build the bitmap on the entire heap page in order to and things together. And so no matter what the limit is over here, we still have that O of in operation, building something that's the entire size of the table. And so this won't get sped up. So even though it's true what you suggested, Kanalu, that if we were able to do an index-only scan, we could definitely take advantage of the limit clause. But even without being able to do an index-only scan, if we can only do an index scan, we can still take advantage of the limit clause with this index right here. So, question?
Would you just like have another, if you had another index? would you-
The question is, in this particular case, how would you do it, or why would Postgres choose to do it?
That is the publisher of the map. Or is it if you have another?
Yeah, so let's modify this here to a situation where it would be very natural to want the bitmap scan, and where then the limit clause would not help us. If we change this to, so our select A, B, C, and now we have two things in our where clause here. We'll say where A equals something and B equals something else. And now we have two indexes, create index on table of A, and another one, create index on table of B. In order to use both of these indexes here to speed up this where clause, we would, the only table scanning strategy that we have, only algorithm that can use multiple indexes is the bitmap scan. And again, it does that by building up the bitmap for each of these indexes, and in this case, anding them together. And if we do that, then we would not be able to take advantage of a limit clause. So then if I added a limit right here, can't take advantage of the limit with the, that's OW, so with the bitmap scan. So in this case, Postgres, depending on how big your table is, if your table only has a small number of things in it, and the limit's not likely to actually reduce things very much, it'll probably still use a bitmap scan. But if you have billions of things in your table, and so this limit is likely to reduce things quite a bit, then Postgres would probably choose to only use one index and do an index scan, so that it can take advantage of the limit and then not take advantage of two indexes at once. Did that answer your question, Cynthia, about where you're... Other questions? Toby?
So, why can't you use the where clauses? what case would you use rum? In regards to the
Yeah, so the question is about the rum versus the gin index, rum versus gin. And the first part of the question, I think, is when are you allowed to use rum versus gin? So what are the requirements for using rum? Are the same as for gin. Anytime you can use a gin index, you can also use a rum index. Just the gin index is built into Postgres. Rum is an extension, so you have to install it. So it's slightly more awkward to work with for that reason, but if it's installed, then you can always use a gin. You can always use a rum index instead of a gin index. And there's really no disadvantage of the rum index. I think that was the second part of your question. If you have the rum index available, there's no disadvantage. No disadvantage to rum. For the same index, it enables more strategies. For the same index, it enables the index and index only scan, which you can't get from the gin index. But it also enables more types of indexes to be created. For example, of like the storing extra information in the index. And so this is kind of like the advantage of a multi-column B-tree index. The analogy is the multi-column B-tree index, multi-column B-tree index. But the syntax is a little bit more weird for it. Was that answering your question? Question is, when would you use the gin index over the rum if there's no disadvantage? And there is no advantage. The only advantage to the gin index over the rum is that it's built in. So if as an example, on your homework assignment, the rum index is not installed on those Docker containers that I gave you. And so you can't use the rum index unless you modified the Docker containers to go through the installation steps of rum. If you did modify the Docker containers to do that, then it would be strictly better to use the rum index instead of the gin index. So the questions about on the final exam, how will this impact things? On the true and false, I might have true and false things that specifically say the question is about the rum index or about the gin index, and you'll have to answer appropriately. If the question is create an index to make this query go fast, then you could use if it requires the multi-column, I guess you should assume that the rum index is installed on whatever database you're using for the final exam. And so if the rum index is needed to do the multi-column stuff, then you would have to use the rum index. If the If a gin index happens to be just as fast as a rum index, though, for that particular query, then, and that could happen because, for example, you have to do a bitmap scan because you're taking advantage of multiple columns or multiple indexes at the same time, then it would be full credit to use either the gin or the rum index. Other questions? Question? Sure. Question is the reviewing the nested loop joins. Let's just talk about all of the join strategies here. And so there's three main join strategies. Anytime you are see a query with a join, three main strategies here. And the one that you should always try to target first of all is the merge join strategy. This again is basically like the merging step in merge sort, and so it has the theta m plus in runtime here, where this is the size of the two input lists of the two tables being joined together, and it does take advantage of the limit k clause here. And so this is the best case scenario for joins, what you always want to achieve. The way that you achieve that is for the inputs to be sorted in both of your tables, input tables, depending on what the column is or what the merge condition is. So I'll write that out up here. That just a quick example of if we have a select and we have from table one, let's say using column A, join, and it doesn't matter what type of join here, so we'll just say left join as an example, that the join strategies are the same no matter what type of join you're using over here. From T using A, left join table 2, like that. Actually, I think the syntax here should be the using A part right here, and this is not actually correct SQL there. And then, so here, the two indexes that we would want to have, that we would want to create index on T1A and create index on T2 of A like this. And this allows us to scan both of these two tables in sorted order, avoiding the explicit sort. So we can easily do the merge join with this join operation right here. The actual question, though, was about the nested loop join. So we'll come up to that here in a second. So merge join, the one that you always want to target if you can. The hash join is sort of, it's kind of an efficient default join that Postgres can do. There's no indexes that you can create that will make this faster or make it cause Postgres to select this. So this is not one that you want to target. This is just something that's there as like a default option that it might have to choose to do. The nested loop join is also one of these default sort of options that we can always use. But there is a situation where indexes can speed that up, and also a situation where it is necessary to do a nested loop join and you can't get to the merge join. And so we'll review that here. So the nested loop join, this is the raw pseudocode for it. It's called a nested loop join because the pseudocode looks like two for loops inside of each other that for each row in A, checking out the row in B, and only if the join condition is satisfied do you output the corresponding row. So this is the slowest possible join right here with our runtime of O of M in. It's like the cross product is what we're potentially computing up here. If this is always true, then the output will be of size m times n, and so our runtime is also mn. Here, I was careful to use an upper bound, big O, and not a big theta here, because if we have a limit clause, this would be very easy to stop early, and so it could be much faster than mn with a limit clause, but this is our worst case runtime right here. Usually though, if we're joining rows together, we probably or very likely have an index on one of these rows, and the nested loop join with an index, the pseudocode looks something like this, where we have only a single for loop, and inside of that for loop, we now use that index to see if we satisfy the join condition. And the idea is that this inner call right here, the find rows B and B satisfying our join condition, that's exactly what this for loop up here is doing. That in this for loop, we're checking each row in B. If it satisfies the join condition, output it. And we're replacing this O of n time for loop with our logarithmic time access to an index down here. And so if we have one index instead of two indexes, then we can do the nested loop join with on that index, and we get the O of m log n runtime instead of the m times n runtime. Normally, if anytime we just have a single join operation, then we should be able to create an index on both of those tables. And so if we have just a single join, we should be able to use the merge join instead of the nested loop join. So key thing about this example over here is there's a single join, and so that implies that we can use the nested loop join. Sorry, it implies that we can use the merge join by creating an index on both tables. Index on both tables implies the merge join is what we want to target. The main situation where you can't do the merge join is when you are joining multiple tables together. So if our join command looked something, well, maybe before I go on to an example with 3 tables joined together, are there questions about anything so far? Why the merge join's ideally better than the nested loop join, or why these are the right indexes for this table combination up here? Great question. So here we are joining 2 separate tables, T1 and T2. What if we join on ourself? So if we have something that looks like select from T1, join T2. I'll do this in multiple ways. It will start with we'll use the on syntax for both of them. on T1.A equals T1.B, like T2.B, and this is A T1 so yeah, the question is about self-joining. Anytime we are joining two tables together that have the same name, we have to provide the aliases for the tables. So this syntax from A space T1, this T1 right here is the alias for the this A table right here. This T2 is the alias for this A table right here, so that when we do the join condition over here, we are specifying that which of these two tables joined together are being joined on. And this A over here is not the A table, it's an A column over here. And in this situation where we have two separate columns that are being joined together, it would look like create index on T1A, and then a separate create index on T2. Sorry, it's not T1 of A, it's A of A, this A being the table name from over here, this A matching that A, this A matching that A right here, and then another create index on A of B. Again, this A matching the table name, this B right here matching this over here. If, and this is because there are two separate columns right here, in order to get sorted results back for both of these tables, even though they're the same table, we need two separate indexes because it's on two separate columns that the sorting will happen. If the query only used the same column, so it's the same query that looked like select from A T1, join A T2 on T1.A equals T2.A, then that would only require one index of create index on A of A, like that. And that same index could speed up both of these parts. Does that answer your question? Does that make sense?
Yeah, I guess just to follow up, so if I have a limit class in the person can't because it's using
So in this case, there are no where clauses, and so the table scanning strategy is going to be well, there's nothing inside of here that's forcing us to use a bitmap scan anywhere. That the table scanning strategy of T1 over here will be an index scan or an index only scan, and the same with T2 over here. That the scan of this table right here will be an index or index only scan on this index. The scan of this table over here will be an index or index only scan on this index down here. So the reason that we don't have to use a bitmap scan and can use an index or an index only scan is because even though we're using two indexes right here for the entire table, for the entire query, in order to scan just a single one of these tables right here, we only need to look at an individual index. And so we only, so there's no need to do the bitmap scan. It also turns out that anytime you're doing a join operation, a bitmap scan is going to be very inefficient because the bitmap scan does not return things in sorted order. And so we would not be able to do that merge join for free. Good questions. Did that answer A question? Other questions about this before we go on to the 3 tables joins and how that relates to the nested loop? Okay, so if our query then looks like select, and we have from A, and then we're joining B, joining C like this. I'll add the using, so this will be column D, using column E like this. Then all of our join strategies, recall, they're all binary operations. They take 2 tables in as input. And so the choice of operations, or the choice of join strategies, will depend on exactly how things get parenthesized here. So if we do a parenthesization like this, of first doing A and B followed by C, so A, B, followed by C, then we'll want to have a merge join happen on A and B. So create index on A, column D. So A right here, column D, followed by create index on B, column D. This will allow a merge join of A and B together here. But after we've merged A and B together, there's no way for us to, well, the sorting, the way that the information will be sorted as the result of a merge join on A and B is that they'll be sorted according to column D over here, because that's the order that the inputs are sorted in. So A, B will be sorted by column D, and we're trying to join on column E. So there's no way for us to do that as a merge join without doing an explicit sort on the results of A and B. So if we're trying to avoid that explicit sort, the best that we can do is the nested loop join on the results of A and B and C. So this right here is the merge of A and B, and then we will take A and B and do the nested loop onto C, where we need to build the appropriate index on C. Build the index on C. And what that will look like is create index on C, column E. And it's column E over here, column E right here, because that's what we're joining C together with the result over here. And that's the best that we can do. We would like to get the merge join because it's faster, but there's no way to get that because the output of this is going to be sorted by D instead of by E. This is one sorting order, or one parenthesization order. The other possible parenthesization order would be first do B and C, and then combine that with A. That'll require different indexes, and so maybe give you a minute to think about what would the indexes, the ideal set of indexes for this sorting order look like. I'll give you a minute to think about that and try to write it down, and then we'll do them. Or if you have questions about what they should be, then feel free to ask them right now. Do you have indexes? Yep. So you have B, E, C, column E, and then the row to create index on for both of those, and that will enable a merge between B and C. The key thing here is that both of these two columns are the same, column E over here. And that's because we'll be joining on column E right here. And then other indexes?
Yeah, just, thinking you an index from the, but that's still uses like the, copy the first one.
Yep, and then so if we do A column D, A column D, that's so this second parenthesization is the syntax in SQL's a little weird that this is what we're joining first, and then we take the result of the thing in green over here, join that on column D with A, and so we need, again, the stuff that's output right here will be sorted according to column E, so there's no way to do the merge join with this on something that's using column D because the output here is E. And so we need to have, so we can't do a merge join, but we could do the nested loop join if we had the appropriate index here on A. And that index means that we need to get A or be able to access column D of A efficiently. And so that's what this index right here is doing. That enables the nested loop join. So yeah, good job. That's the correct set of indexes for this parenthesization. In order to, the most likely sort of question, and the question that is on the practice exams related to the multiple joins like this says something like create indexes that will make the query go as fast as possible. And in order to answer that question, you would have to create indexes for both possible parenthesizations like this. In Postgres and in most database systems, you don't manually specify the parenthesization. The database does that for you based on its internal heuristic of which way is going to be faster. And so you need to be able to support either version of this, make either version go fast. And you can do that by, you'd create both the indexes up here and the indexes down here. In this case, and in every case, when you have this situation, you'll have a number of duplicate indexes. So here the CE and the AD are duplicated between both of these two join orders. And so there's no need for creating those indexes twice. So there'd only be a total of 4 indexes that you need to create in order to answer the question of how do you make this SQL query go as fast as possible. You need everything from the top and then just the unique things from the bottom, which is just this first one right here. And then the CE and AD are duplicates, so you wouldn't write those twice. Any questions about that? Your question is, does the order of the create index commands matter? The answer is no, the order of create index commands never matters. Anytime you run the create index command, it will just be added as an index in Postgres and maintained in the same way. I believe the internals of how Postgres decides to update the index is that it will do the updates of the index in the order that you created them at. but because of the ACID guarantees of Postgres, that's not something that's observable to the end user at all. And so as an end user, you can't actually know what order the indexes were created in.
But you can have like multiple colors or order the colors.
So yeah, if you, the order that you put these commands in does not matter, but if you change the commands themselves to have, say, multiple columns, then the order of those columns will matter. Yeah, that'll actually physically create a different index doing something different. Postgres won't stop you from creating multiple indexes, and it'll just maintain both of those duplicate indexes, but there's no performance advantage from creating multiple ones. Let's see. Let's think about, is that a question? Or
Yeah, I was looking at one of that, is it,
Mhm.
it's a lot of text, I think, using it to attach it to, and just make the syntax. Something like,
yeah, off the top of my head, I don't know the syntax for the attaching the rum index as well, and so that's something that I would have to look up to write out the answer for. But let's take a look, or let's think about, so we've talked about the join strategies, and we've talked about or we've had a SQL query that has joins, and we've had a separate SQL query that has a where clause. What happens if we have a query that has both joins and a where clause? So something like, we'll do select A comma B from table 1, join table 2 using column C, where D has some condition attached to it. And we'll do it, some user-defined condition like that. Then how would we write our queries to, and I want this to be an actual equality instead of an inequality, D equals value. How would we write our new indexes to handle both the join and the where clause at once? Anybody have any ideas? Go ahead.
like, the index of table, you want on the
So create index on, say, and then what? D comma C. Okay. Any other indexes? T2, D comma C, like that. Okay. And so what these indexes would do is that it would allow us to first use this where clause here to filter on our tables, and then get the results ordered by the C column over here. So we're having our equalities, whatever our equality condition is over here, those will come first. And then we're sorting something over here with these C values because we need them in sorted order as input to our join clause over here. In this case, we have the D here in both of the indexes, T1 and T2. And this is assuming that the D clause or the D column here exists in both tables. assumes D exists in both tables. That's what you would want to do, exists in both tables. If D exists only in one of the tables, then we'll say that if D is only in T1, then you would want the same first line. Create index on T1, D, comma, C. But then the second index would be just T2 of C like that, because there's no D that you can filter on before getting the C value out here. If there was another column in your where clause over here, something like E equals colon value, then if E and D are both in the same table, you would include them in the same index. If they're in different tables, then you would include them in whichever indexes are appropriate. But in general, you want your whatever equality constraints you have, those would still come first. And then your sorting, whatever you're sorting by, would come immediately after the equality constraints. With these two indexes right here, either the blue or the red, that would allow us to do an index scan, getting the results out in sorted order. The index scan, again, gets the results in sorted order. A bitmap scan could not get the results in sorted order. And we have two indexes, but we don't have to do a bitmap scan because each index is only being applied to an individual table. The bitmap scan you only need to use when you have two indexes that are applied to the same table. We could further make this a little bit more efficient into an index-only scan. We could get index-only scan by including the A and B columns, by including these A and B columns in these indexes. Index-only scan by including A and B in the index wherever it's appropriate. And so it would look something like create index on T1, D, comma, C, comma, A, comma, B, like that. And same thing down here, T2 with C, we'll do C, comma, B like this. This particular combination right here, that is assuming that table 1 has all columns, table 1 has all the columns, and then table 2 does not have the D or the A column. But in general, you want to include every column that that you might need in order for the index-only scan to happen. And the order is always the equality constraints. You have one column that you can do the sorting on, whether in this case, there's no explicit sort because there's no order by, but we need the sorting for the input to the merge operation up here. And so that's what the C column is our sorting column. We know it's C because it's inside the using constraint right here. And then the auxiliary columns that are just for information purposes only on the outside over here. Any questions about that? Rosie? Yeah, if the where clause over here was an inequality, then we run into the same problem that we had before of we have two things that we need sorted by, the inequality and the using constraint. And so if the inequality was something like C greater than or equal to something, this poses no problems. No problems because the inequality matches what we need to be sorted. because the inequality and sort column are the same. But if those were different, then there'd be no way to handle efficiently both the inequality and the sorting at the same time. So I'm not on the final exam, I'm not going to ask about a situation like that in the real world. You would probably generate indexes for both situations and let Postgres pick which one it thinks is going to be fastest. Either that, or you would have to redesign your schema in order to so that the query doesn't have that problem. Question?
Yeah, so you said this one is the index.
So the bottommost green down here is the index only scans. In order to be able to use the index only scan, every column, no matter where it appears in the query, must appear in an index somewhere. So these A and B, they don't appear in the join or the where clause. So they need to be included in the rightmost part of the create index statement in order for the index only scan to happen.
It's not the index that we stand for the total pages access, that's zero.
The question is, so if we come over here, just making sure I got the question right under the so I'm just saying index only scan here that's saying that the table pages accessed is 0. That's where the name index only scan comes from because it only accesses the index and not the actual table itself. But the index pages accessed over here is this complicated formula. And if you look at the index pages accessed formula here, that'll be the same for the index scan and the index only scan. The performance difference between these two scans is only how they access the table itself. So they'll access the same index pages, just different table pages. For the index only scan, the reason why the table pages accessed is 0 is because all the information is inside the index. So there's no need to access the table in order to get the information. If we have a multi-column index, so create index on T, A, B, C, all three of these pieces of information get stored in the index, in each row in the index. And so there's no need to access information from the table. There's a caveat to that, though, that if you recall from the details of how the pages are stored in the index versus the heap, that the index pages do not store the index pages do not store the transaction information. So TX for transaction information. And this is needed to ensure that the right rows are visible. Ensure the right rows are visible. And so if Postgres detects somehow that an index must, or a value in the index must be visible to all possible transactions, it will not access the table. If it needs to determine whether a row is visible to the transaction or not, then it will access the table to determine that. The way that it knows whether things are visible or are not visible is what the vacuum process was doing and the visibility map. The visibility map is the list of just 0 and 1s for each page that it's just keeps track whether every tuple in that particular page is visible to every transaction currently available or not. And so if the visibility map says the results are visible, then it won't access the table page. If it says they may or may not be visible, then it will have to access the table page, not for the column information, but for these system columns up here, the xmin and xmax, to know whether the transaction is visible. So if you have run a vacuum without doing any subsequent modifications, then table pages access guaranteed to be 0. Does that answer your question? So that's our official end of time. Happy to stick around and answer a few more questions if people have more questions. I would not expect the final to be curved. Do you have a question, Ian?
I have a question on the indexes.
Okay. I'll take a look at that in a second. Maybe, yeah, last hints about the final are just, on the true and false, very easy to lose points by being overconfident and selecting answers that are not correct, and you get the minus penalty. So make sure that you double check those. And yeah, and the hard part, there's a lot of things on for both sections of the final exam, and a lot of weird interactions between all the different systems here in Postgres. So I think that's hard to keep all that stuff straight, and so try to keep it straight. As helpful advice as that is, not helpful at all, probably. Yeah, Kunal.
Regarding so we can use electronic resources, what can we not do?
Question is, what can you not do? You cannot use the electronic things to communicate with other humans during the exam time. So that means the obvious thing of communicating with other classmates about what is the answer to number 2. Means no posting on Stack Overflow, asking here's the setup to the question, what's the answer? But if you are Google searching and run into a Stack Overflow question that somebody else asked, feel free to do that. Basically, you can feel free to ask ChatGPT whatever the question is, see if it knows the answers. Anything where you're not providing information to a human about what's on the test is fine. It would be acceptable to post things to Stack Overflow in preparation, or to ask me things in preparation before I give you the final, but not after the final's out. Does that answer the question? Okay.
So when we're doing the indexes part, our indexes that we created in previous problems, they don't apply to the future problems.
You should think about each problem being fully independent of every other problem. And so one thing that we didn't talk about at all is this first problem up here with these the indexes that are automatically created, the unique indexes up here. You should think about this problem, whatever the indexes that are being created up here, these ones exist throughout all the problems because they're part of the schema. Then the other problems down here are on their own. And if you created an index for problem 2, you don't need to think about whether that exists or not still for problem 3. Does that answer the question? Sure. Go ahead.
So in the first seven, it says construct these questions of the says construct indexes to all fair to the next one scan, and the users use from column.
Sorry, this one right here.
This number 7 is the integrate. So what does it mean by creating indexes so
So here, yeah, it's something that we didn't talk about at all today, that anytime you have the unique constraint, there is a corresponding index for the unique constraint. And so the way that you create unique constraints, you can either do it in the schema definition of the table itself, just adding the unique keyword like we were just looking at, or you could do something like create index, sorry, create unique index, unique index on users username. This right here is the same as if we had in our create table users command username text unique. There's no difference at all between using this syntax here or this syntax here. They both do exactly the same thing under the hood. This is just a shortcut for this up here. What this problem is getting at, though, is that here we would like to be able to do we would always like to be able to do an index only scan. Here, though, if we have this index like this, that's not going to allow us to use an index only scan because there's this created at column right here. And so the next thing that we might be tempted to do is, I'll write it up here, we would might do something like create unique index. My legibility of my writing is very bad right now. I apologize. That's create unique index on users username comma created at, something like that. This would enable an index only scan of this query down here, but this unique index has a different semantics than this unique index down here. It's saying not only does the username have to be unique, but it's okay if there's duplicate usernames as long as they have different created at timestamps. So this is semantically probably not something that we would want, a constraint that we would want to enforce. This would be a better constraint to enforce. So rather than having this be a unique index up here, this is not something that we would want to do, that semantically combining this red index with this orange index is semantically what we want to have happen. This, though, is duplicating information. It's creating two indexes, one that satisfies this unique constraint, and that's the only purpose of this index, and this other index up here that has both the username information and the created at. So it's a little bit inefficient from a maintenance perspective that we have to maintain two indexes, and it requires twice the disk space because we're creating and maintaining two of these indexes at the same time. So the solution to this problem right here in green would look like create unique index on users username. So only have the unique constraint enforced on the username portion of the index, but then there's this additional keyword of include, which says that we will be including other information in the index, but not enforcing a constraint on this index. Include created at. Like that. And this now, in terms of the physical structure of the index, this green index and this red index are 100% physically equivalent to each other in terms of how the data is stored on the hard drive. Each row in this green index will have both the username and created at columns inside of it. And so it enables the index only scan down here. It also is semantically equivalent to this orange index down here in terms of the unique constraint, because the unique keyword right here, this unique keyword only applies to the username column and does not apply to the created at column. So this include keyword allows us to combine this red query up here with this orange query down here into a single index, saving disk space, saving maintenance operations on inserts, updates, deletes, but still getting the unique constraint and still getting the index only scan. Any questions about that? Any last questions about the final?
Like more general.
Sure.
Efficient to do a multi-column index than create multiple.
So the question's about, so here we have a multi-column index. What if we had just two different indexes on? In this particular case, there is no multiple set of indexes that we can use to speed things up. We could only use multiple indexes if there were multiple conditions in the where clause down here, in which case we could take advantage of multiple indexes. That's if you have multiple indexes that you're using on the same table because of the conditions in the where clause, that forces you to use the bitmap scan option, which is generally going to be less efficient than the index or index only scans. So if we said had a web page that was running a known query many times, we would try to design an index that's going to avoid the bitmap scan and only do the index only scan. But if we're just running a one-off query, then it's okay to take advantage of the bitmap scan and not create the special index for multiple columns. Did that answer your question, sort of? Everybody's going to ace the final? Good answer. Okay, then yeah, I'll take a look at in your thing. Oh, sorry. Yes, we will clear out of here.